Okay, in lesson 4, we're doing another example in heat transfer, and this time we're practicing heat transfer through a wall. So we're going to have conduction and convection on two sides of the wall. Let's assume we have a wall. If I can draw, so let's try to draw a wall. Assuming this is a rectangle, I'm going to apply a heat or a temperature of let's say 60 to the interior, give a K, which is conduction coefficient of 100 again to the wall, and on this other side of the wall I'm going to say that there is convection with a coefficient of 20 and temperature of, let's say, 30. And I have to mention that this temperature, T infinity, is not the temperature of this side of the wall. Perhaps this is the temperature of the air or any other fluid that is flowing around this area, through which convection heat transfer takes place through the wall. So if the thickness of the wall we assume is 1, and let's give a length of maybe 20 to the total length of the wall, I'm gonna have a 1D conduction through the wall in x direction, if my x direction in this orientation. And then from this side of the wall there's going to be convection heat transfer to the air or the other any other fluid which is in the environment outside this wall. So basically, through the conservation of energy, in this wall, which I'm going to call wall 2, at wall 2 conduction heat transfer is supposed to be equal to convection heat transfer. K times delta T over delta X, which I guess you know that there is a minus over there, is equal to minus H delta T. And this delta T is not the same as this delta T, so I'm going to put TW here. The minus signs are going to cancel out, so 100 times delta X is going to be 1 in here, so I'm going to put 1. 60 minus T2 is going to be equal to 20 times T2 minus 30. And from solving this equation we can find T2, which is the temperature of the wall in this side. So 6,000 minus 100 T2 is equal to 20 T2 minus 60, or 600. So moving them to the other side, 6,600 is going to be equal to 120 T2. So T2 is going to be equal to 6,600 over 112, or 6,600 over 120. From solving this equation we can find T2, which is probably going to be 55. And then if we have T2 from this equation, from Q equals 100 times 60 minus 55 over 1 is equal to 100 times 5, is going to give me a heat transfer of 500. And also Q equals 20 times 55 minus 30 is going to give me 20 times 25, which is again equal to 500. In this example, the other technique of ANSYS I'm going to teach is defining a path and mapping temperature to the path and plot temperature versus distance or length in the wall, which, because I'm doing a 1D heat transfer, I'm expecting to have a linear, if this is my X and this is temperature, from 60 to probably 55 in here, I'm expecting to have a linear difference in temperature or gradient in temperature from x0, which is here, to x1, which is going to be here. So with this, let's go to ANSYS and do the demonstration. Okay, we're in ANSYS right now, and I'm going to select preferences and check thermal, click OK, come to preprocessor, and again the first step is to define my elements, add an element, and from thermal I'm going to pick solid, and this time again I'm going to pick plane 77, which has 8 nodes in square shaped elements. Close this, and this element does not require any real constant, so I can skip that one and come to material properties, material models, click thermal, conductivity, isotropic, and give a conductivity of 100 over there. Click OK. Then I can come to modeling, and I want to create an area of rectangle shape. So I come to areas, rectangle, by dimensions, I'm going to give 0 and 1 to x. Or let's make it from minus 0.05 to 0.5, which gives me the same length, and from minus 10 to 10. This will give me a rectangle of 1 units in x direction and 20 units in y direction, but the center of this rectangle will sit at the point 0, 0. Click OK, and as you see, the origin of the coordinate system that I'm using for this analysis is exactly at the center of the rectangle. I can go to meshing, and again I'm going to use mesh tool, and smart size, let's say 4, click mesh, select my area and click OK, and my sample or my model is being meshed. Now I can apply the loads. Come to here, make sure that I'm doing a steady-state analysis. Let me close this window. OK. Define loads, apply. I'm going to apply thermal loads. So the first thing I'm going to apply is temperature on this line, which we said we're expecting that to be 60. Okay. And I'm going to apply convection on this line, which it takes from me the coefficient, which I said I want it to be 20, and the temperature, the bulk temperature, which is the temperature of the air or any other fluid on the other side of the wall. I'm going to give it 30. Click OK. And just to make sure that there is no heat flux on the top and bottom of this rectangle, I'm going to come here on lines and select the 2 lines on the top and the bottom of this rectangle and give a 0 value for that. Click OK, and my model is ready to be solved. So I come to solution, solve, current LS, yes, solution is done. So for this model, let's see how is temperature changing. Plot results, control plots, nodal solution, temperature. So the minimum is 55 on the wall, and the maximum is 60. So the temperature is changing from 60 to 55 as we had calculated before. And thermal gradient or thermal flux in x direction is 500. Again, the same thing that we found out in the analysis by hand. So basically everything is the same or similar to what we had done in the previous 3 lessons. And if I come here and I want to see the vector plot of heat flux, everything is in the x direction, which is what we were expecting. But let's have or right now I want to define a path. So I come to under general post process, I come to path operations, define a path. I can define a path by nodes or by on working plane or by location, because here I defined my rectangle to change from minus 0.5 to plus 0.5 in x direction and minus 10 to plus 10 in y direction. I know that this middle is at x equals minus 5 to minus 0.5 to plus 0.5 and y equals 0. So I can pick by location, define a path name. I'm going to say path 0, 1. Number of points I want to define for this path is 2, the beginning and the end. So that's it. Number of data sets, let's change it to 40. And number of divisions, let's divide that to 80 and click OK. This number of divisions makes the reading of data pretty more precise than lower numbers for the number of divisions. So point 1, so in this window, NPT path point number is the number of point that you're defining the locations for. If you remember, I said I was gonna define 2 points, the beginning and the end for this path. So point number 1 is gonna be the beginning. I'm gonna say from x of 0.05 or minus 0.5 and y of 0. Okay. To the point number 2, and remember that you have to change this number manually, otherwise ANSYS will overwrite your data. So point 2 is located at plus 0.5 and y equals 0. I can now cancel this window. So this path at the very center of the rectangle is defined for me. Now what I have to do is to come and map onto path. On the map onto path, I want to map the temperatures, and I'm going to give it a name, Temp 1, just to make it different from Temp, which is written in here, and click OK. You can map onto the path as many items as you want or as many results as you want, but here we're only having temperature, and if I go to flux and gradient differently, this is not going to help me a lot, and I'm not very interested in those things, so I'm just going to stick with temperature. In future examples, I can go on and map more results in my path and plot them. Now here, after defining the path in define path command and mapping temperature onto my path, I can come to plot path on graph and find the variable that I defined earlier and click OK. And as you see, from distance of 0 to 1, which is at the interior and the outside of the wall, the temperature is changing linearly from 60 to 1. We can also extract this data into a text file. So if I come to list results, path items, path 1, okay, and select temperature 1 that I selected earlier. I can save this file now and plot this in Excel or any other software that can read this file for me. So there's a data point. S represents the distance from x equals 0, which at 0 it represents the interior side of the wall, and when it goes to 1 it represents the wall, the exterior of the wall. And the number of divisions that I made, which was 80, means that this distance is divided by, every increment is 1/80. And the temperature for each of them is red and represented in here. And I think this concludes lesson 4. A very basic heat transfer with conduction and convection, 1D conduction and free convection of the wall. We found the temperature which was unknown to us on the exterior side of the wall, and we also found the heat transfer or heat flux which was going through the wall, and also the convection heat or heat conduction or convection. And we also defined a path and mapped the temperature on the path and then plotted that temperature. The only thing that you can probably do is go on geometry and click that one. As you see, it's kind of like a representation on how temperature is changing, but it's not as clear as on graph that we did earlier. So with this, I'm going to conclude lesson 4.